Hi, I'm Pete Harris, and welcome to this talk on boosting graphics performance on Mali made easier. I'm Technical Director for the ARM Mobile Studio tools. ARM Mobile Studio is our set of Android performance analysis tools, targeting ARM CPUs and Mali GPUs for graphics profiling. They're designed for application developers. They run on consumer devices, and root access is not required. And the real power of these tools is they can give you system visibility. You can see workload scheduling across the CPU and GPU and across the different GPU command stream queues. One of the primary tools we have in these is performance counters. These are hardware events that the hardware counts as the application runs and give you very good visibility of what's going on the device. And one of the main questions we get is, this is all wonderful, very rich data, but what do they actually mean? So this talk is going to be a lightning tour of the Mali GPU counters. We're not going to have time to cover all of them, so we're going to focus on the command queue to shader core data path, which is the main route for running shader programs on the core. This talk is going to assume some knowledge about graphics and basic GPU functionality, and we'll assume a little bit about tile-based rendering as well, but we'll cover the essentials. If you need a refresher or want to learn more, please go and check out some videos that we have on our portal, which will give you a ground-up introduction to GPU and mobile rendering. So the Mali GPU is made up of 4 block classes. We have the GPU front end, which takes the input requests from the CPU, the command streams, breaks those into tasks that are dispatched to the various processing elements on the core. We have the level 2 cache, which handles the kind of unified data cache for all the GPU data. It's also the interface out to DRAM. We have the fixed function tiling unit. This handles the geometry pipeline, primitive assembly, clip and cull, as well as the tile binning process that we use for tile-based rendering. We then have the shader cores that are responsible for actually running the shader programs and producing the output that the GPU generates. We have a set of counters for each of these blocks, and the Mali GPUs can capture all of those counters simultaneously. So you don't have to pick and choose which counters you want to capture. Depending on the GPU design that you have, you may have 1 or more cache slices and 1 or more shader cores, and the tool has to make a decision about how to present that data. For our Streamline profiler, for the level 2 cache, we count the sum of the counters across all of the blocks. This gives you correct totals for things like memory bandwidth and memory system stalls. And this is important because memory bandwidth is one of the most power-hungry things that the GPU can do. For the shader core, we count the mean of the cores, the average, and this allows us to compute speed of light throughput compared to GPU frequency or shader core frequency. And generally, that's the most useful metric that you want for the shader cores to show which unit's the most heavily utilized. In this talk, we're going to present it as some block diagrams. These diagrams are based on the Mali G78 GPU that you get in ARM Mobile, and the counter names are from ARM Mobile Studio 2021.3. And we're going to present them as variable names that you can just cut and paste and drop into Streamline expressions. And the first set of things that we have are a set of constants, which you can use to understand how many cache slices you have in a particular GPU, how many shader cores that you have, and the width of the output bus to memory so that we can convert bus cycles into a byte bandwidth calculation. Before we get into the detail, as always with Streamline, one of the first things that we would always recommend is starting with a template. So a template is a pre-designed visualization that comes from our tools team. And if you pick the template for the GPU in your device, you will get a designed visualization and automatically select all of the counters that GPU template requires. However, you can customize this with advanced counters. You can either drag and or double click more counters across into the events to collect column. And if you toggle the advanced counter button on the title bar there, that will unhide some counters that are a little bit harder to use, a little bit harder to interpret, but may give you some slightly richer data that you can go and play with. On the visualization side, same trick applies. We would recommend starting with a template. So once you've captured your data, what you will get by default will be an alphabetical visualization, which isn't the easiest to use. So reselect the template that you use to capture with, and that will give you that designed visualization that will walk you through the data in a step-by-step fashion. Templates are customizable, so you can add your own charts, you can add series, and for the series that you add, Streamline contains a rich expression language, so you can do multiplication, addition, min, max, scale things to percentages, and so on. So you can compute more easy to understand metrics based on the raw counters rather than just presenting everything as absolute cycle counts or event counts. Once you've customized a template, you can save it as a custom template, and you can then share that with team members, and you can use that template in the counter selection workflow. So you can kind of design it once and then reuse that over and over again for repeated analysis. The counters that we have really try and fit 4 workflows: 2 for system behavior, 2 for content behavior, and different sets of counters are useful for the different workflows. On the system side, there's really 2 behaviors that we're interested in. One is scheduling. So how is the GPU being used by the application? Are we getting, the first question would be, are you actually GPU bound? Or is your bottleneck on the CPU or somewhere else? The second question then is, are you getting good parallel execution? Tile-based rendering runs workloads in 2 pieces, geometry and fragment shading, and you really want different render passes to overlap the vertex shading and fragment shading to get the best performance through the shader core. The second part on system integration is the memory system. Again, memory bandwidth is one of the most power-hungry things the GPU can do. So you want to look at the bandwidth you're consuming, back pressure from the memory system, memory latency, because controlling your data access more than your shader code is one of the most important things that you need to do. On the content side, there's 2 parts to it. One is trying to understand the workload the application is submitting to the GPU and trying to understand why it's below performance. It could be because of inefficiency, the application not following best practice, lots of geometry that's being culled because it's behind the camera, for example. It could be slow because of complexity. The application's well written, but the complexity of lighting calculations or rendering calculations is just too high for the performance of the device that you're targeting. And this can be a particular issue when porting high-end content to mid-end devices to widen the target market. The other part can simply be size. The workload could be simple, could be well written, but there's simply too many vertices, too many pixels, too many frames per second. And this can be a real issue for entry-level devices where you may only have a single shader core. So you really have to be very, very careful how you spend those cycles. And depending which issue you hit at that point, that will inform what kind of fixes you need to go and apply. Are you looking to optimize shader code? Are you looking at simply reducing frame rate or reducing resolution as a more brute force way to reduce the workload? For shader limited functionality, where you're just looking to squeeze some performance out of an existing rendering algorithm, you generally want to start looking at GPU critical path analysis. And this is really about trying to identify which units in the shader core are being most heavily used by the shader code. Ideally, they all run in parallel, so the one with the highest load is normally going to be your bottleneck, although optimizing the other ones is still a worthwhile goal for energy efficiency. So this is the sort of data path block diagram for a Mali GPU. We have the 2 queues, non-fragment and fragment, on the front end. So these take the command streams from the application and dispatch them down through to the hardware units. The non-fragment path can either go straight to the shader core for things like compute workloads, or it can go through the tiler for geometry processing workloads. The shader core takes tasks. So these are small pieces of a draw call and has a front end that will turn those into warps to execute. The execution core actually runs shader programs, and then the fragment backend handles retiring completed tiles, writing the frame buffer back to memory. For each of the major blocks here, we have an active cycle counter. So this will increment any cycle that block is doing something useful. However, this does not tell you about throughput. This is purely something in the block was making some processing. So active counters generally tell you about scheduling behavior. Were we successfully keeping the execution core busy, even if the execution core units may not be loaded because of the style of the workload? We have a similar set of active counters for the 2 data paths rather than just the functional blocks. So here we can see the utilization of the non-fragment queue and the utilization of the fragment queue. And again, this is really trying to tell you about scheduling behavior. If you're getting good overlap, then you should find your dominant queue is very similar to your GPU active cycles, for example. One useful trick at this point is to look at some workload counters. The fragment tasks that we dispatch to shader cores are 32 by 32 pixels in size. So if you scale the fragment tasks by 1024, then that will give you the number of pixels being shaded by the fragment shading. So you can divide that by frame rate and get a feel for number of pixels per frame that are being shaded. The shader core itself is a programmable core wrapped by these fixed function front ends that generate warps and the retire path for the fragment shading side. And we have counters that can show you the behavior as workload flows down this pipeline. So we can count the number of rasterized primitives being read. We can count the number of quads, so 2 by 2 pixel regions coming out of the rasterizer. And importantly, we can count the number of those quads that are partial. So these are 2 by 2 pixel patches where some of those pixels don't actually contain any active coverage. And that can be a real issue if you've got very small triangles. Lots of partial quads being rasterized is a direct efficiency loss for your fragment shading. So try and keep triangles as big as you can. We can look at the dispatch through early ZS in terms of testing and the number of things killed by early ZS. Things killed here aren't really a problem. It's being killed before fragment shading, so it's not going to cost you a huge amount in terms of energy. But you do generally want to see as much of your workload as possible going through early ZS testing. If you're having to fall back to late ZS testing, that's much more expensive if you start killing things because you will have done at least some shading to get to that point. We can then count the number of warps that get spawned. For this particular GPU, warps are 16 wide. So if we multiply those by 16, that gives us our number of vertices and number of fragments that are being spawned per core, if we assume the warps are full. And we can also count the number of tiles being shaded. Tiles are normally 16 by 16 pixels for this GPU, but they're not always. If you have a very high amount of per pixel storage, you may find the tile size drops. So for counting pixels, we would still recommend using that top level counter from the drop manager. There are some useful workload stats we can pull out from the pipeline. We have a hidden surface removal scheme called forward pixel kill, and so we can count the number of quads that go into that survive early ZS that are valid occluders. So they're opaque, they have known coverage. We can use those to drive our hidden surface removal scheme. And you want to make that percentage as high as possible because hidden surface removal is a very good way of removing redundant work. We have a buffer of quads called the forward pixel kill buffer in front of the execution core. This will be active any cycle there is at least one quad in that buffer. So if you see that percentage being a low percentage of your fragment active time, that can be a good indicator that you're struggling to rasterize and early ZS test things fast enough. So very small triangles or pixel dependencies on ZS testing, holding back work and not keeping that buffer full. So again, that can be a good indicator for best practice violations and content efficiency. On the tile write back side, we have an optimization that can skip tiles if they match the content already in memory through a CRC check. For 2D games in particular, that might give some optimization scope for doing a partial render of the frame. So that counter gives you some indicator that there could be some optimization opportunity for that. We have a number of bandwidth counters. These count the number of bus cycles, multiply them by 16 for the internal bus to get your bandwidth. And for reads, we can tell whether data came from the L2 or had to go out to an external memory fetch. So you can see how well the L2 cache is working. And if you look overall with some of the other counters we'll look at later, that tells you your breakdown of where your external bandwidth is coming from. Is it geometry? Is it texture? Is it fragment setup? Is it tile memory? For the programmable core, we have a warp creation unit that will create the warps to run. We have the processing unit, which contains the instruction cache and the various arithmetic pipelines, and a number of fixed function units that process offload work from the processing units. So we have a load store cache, which is a general purpose read-write cache, mostly used for geometry access, spilling to stack, and so on. We have a varying unit, which is a fixed function interpolator. We have a texture unit, which contains the texture cache, the compressed texture decompression, and the filtering unit for bilinear, trilinear filtering. And we have a fixed function LateZS and blend unit for doing LateZS testing and retiring completed fragments out to the frame buffer. In this unit, only the load store cache and the texture unit talk to memory. If for geometry data for the varying unit, that data will get fetched through the load store cache path. The first set of counters that we have look at warp creation. So as we saw in the previous slide, we can count the number of warps being created for fragment and non-fragment workloads. We can also tell how many of those warps are full. So they contain a full complement of 4 work item patches, either 2x2 pixel quads or 4 vertex blocks. So if you have non-full quads, that again could be an indicator that you can't rasterize fast enough or dispatch vertex shading fast enough to keep those full. We can also count the number of quads that use the full register allocation that's possible. So Mali GPUs for the Bifrost and Valhalla family can either use less than 32 registers or 33 or more registers. And if you use the higher register allocation, you halve the thread capacity of the core. So a high percentage of all register warps could be an indicator that you're not running the cores as efficiently as you could, and that may impact memory latency hiding ability. We can look at the processing unit, the number of instruction cache misses, the number of diverged instructions for control flow divergence. And here we get our first speed of light measure. So we can issue 1 instruction per clock through the pipelines. So if you add together those 3 instruction issue counters, that will give you your speed of light throughput for the arithmetic units. And that will be our first speed of light measure for an actual functional data path that we want to keep busy. The varying unit is quite simple. We have 2 counters that will count either 32-bit or 16-bit interpolations. Add those 2 together, that gives you your varying unit utilization, number of cycles that it's busy doing interpolator. For the LateZS and blend unit, we don't have any data path speed of light counters, but we can count the number of quads doing LateZS testing and the number of quads being killed by LateZS testing. Again, LateZS kills happen late, so you've done some work before you start throwing them away. So you really want to try and minimize the number of LateZS kills that you are triggering in your application. For the texture unit, it's a little bit more complicated. So effectively, the kind of architecture of the pipeline is to have some descriptor cache where we go and fetch the metadata about the textures and the surfaces and the samplers that we need to use. And then that goes into the texture data cache to actually fetch the data we need to complete the operation. Those may miss in the cache. So we have a parking buffer that can sleep threads while they are waiting for memory. And then when we have the data, that then goes into a filtering unit. And for the Valhalla GPUs, Mali G78, that's a 4x unit. So we can do 4 bilinear sample filters per clock cycle. There are 3 possible bottlenecks in this pipeline. The input bus, so if you have a texture operation with lots of operands. The output bus, if you have lots of high P vec4 samplers returning very high precision data. Or the filtering cycle, if you're doing complex filters, trilinear filtering, anisotropic filtering, where you need to do a lot of filtering per request. So the speed of light for this pipeline is the maximum of the input bus, the texture active cycles, and the output bus. For the 4x unit, we can count the number of cycles that the filtering was actually using the 4x width available, either a 4x bilinear operation or a 2x trilinear operation. And if you're not hitting that path, that could be an indicator that you're struggling to pull data out of the texture cache. So 32-bit, or greater than 32-bit per pixel data formats, for example. We have the same set of bandwidth counters, so we can count the number of read beats and from L2 and from external memory, multiply by 16 to turn those into a byte calculation. Here you can do interesting things like count number of read beats per texture request, which gives you an idea for how much data you're needing to complete your requests. And if you know you're using compressed textures, etc 4-bit per pixel, you would expect that to be about a half. And if you don't see that, then that could be an indicator that you forgot texture compression or you forgot mip mapping, and you're having to fetch more data than you really should be. For the load store cache, we have a cache line wide data cache lookup, and it's the data cache lookup path that's normally the critical path. The counters here are counting the number of cycles that we were using the data cache path for reads or writes, broken down by the number of requests that we're using the full width available and the number of cycles that we're only using part of the data path if they weren't fetching a whole cache line. So the critical path for this pipeline is simply the sum of the data cache cycles, and so that would be the speed of light for the cache. The load store pipe also handles atomics. They pipeline, but they're reasonably tricky to interpret. So you can count the number of atomic access cycles, but it kind of runs in parallel to the load store cache lookup path. Because the load store cache is read-write, we have two sets of counters here: input reads broken down by L2 or external, as well as the number of output bytes. There's two separate output counters for different reasons. For application, you need to just add those two together, and that will give you the total bandwidth out of the load store cache. So for this talk, we have shown the subset of Mali performance counters just for shader core dispatch. So this looks at how we take a command stream in at the front end level and kind of get it down to running code on functional units in the core itself. There are other counters we just haven't talked about today, in particular for the geometry path and for the memory system. We'll try and fill some of these blanks via some YouTube videos after Dev Summit. We've shown where you can get data for the speed of light calculations, so which units are the critical paths. Those are the ones that you should target optimizations at. We've also looked at the counters that you can potentially start using for some of the best practice measures. So bytes per texture lookup, how well is my cache working? Am I getting lots of early Z testing, which is good? Or am I getting lots of late ZS kills, which is bad? Right. And so the counters can start guiding you towards the optimizations that you need to be applying. For next steps, we have so these QR codes are direct links to some pages. We have the on Mobile Studio tools. They're free to download, contains the Streamline profiler, but a number of other tools too, such as Graphics Analyzer and the Mali Offline compiler. We have a datasheet, which is a kind of quick reference card for all of the recent Mali GPUs that contain key speeds and feeds about the GPU. That can be quite useful for things like warp width. We had a 16 wide constant here, for example. You can go and use the datasheet to look up some of the other constants that you might need if you're customizing expressions. We also have a number of counter guides, one per GPU, that will walk you through the GPU template that we have in Streamline and explain how we expect those to be used. In general, we have lots of developer education material on our developer portal. So to learn more, please go to developer.arm.com/graphics. There's a live Q&A session starting now to continue the conversation. To take part, join us on Zoom by clicking the yellow button just below the video player on this sessions page.